All right. So welcome, everybody. My name's Lisa Couture, and this is a talk that's for the data science program and also for the CS Distinguished Colloquia. We're extremely pleased to have Ben Shneiderman visiting us. He's a distinguished university professor in the computer science department at University of Maryland, where I was for 12 years, and so that's how I know Ben, and know Ben both as a mentor, colleague, collaborator, and we're extremely pleased to be able to entice Ben out to California to come give a talk, in particular to present the aspect of, and a very important aspect of data science, which is how do you get the user involved in the process, how do you understand the problems that you're working on, and Ben has spent his career looking at this at a whole variety of different levels. And of course, that wasn't the only reason he came out here. It turns out he also has some grandkids that are nearby. So, but we're pleased and we're happy with the kind of diversity of the audience. So I very much hope that you guys will stick around a little bit afterwards and actually, talk to each other a bit. It's nice to see this kind of mix of people from different departments and different schools. So. We already have some of the important distinctions of Ben up here, but first off, he's a fellow of the AAS, ACM, IEEE, a member of the National Academy of Engineering, and this is all in recognition of his pioneering contributions to human-computer interaction and information visualization. He's made a number of important contributions, including very basic things like direct manipulation concept, the clickable web link, and many others. One of the more recent things that he's been working on that I don't think he's going to talk about here is NodeXL, which is a system for understanding and visualizing graphs. This is one of his most recent books. He's written quite a few books. One of his books, Leonardo's Laptop, appeared in October 2002 and won the IEEE Book Award for Distinguished Literary Contribution. I think that you'll find his style and his thoughts very engaging, and we're very pleased to have him here.
Thank you. Thank you for that warm greeting. I'm very pleased to be here to join Lisa and other good friends and buddies like Ike Massey and some familiar colleagues. And I'm very happy to be back at Santa Cruz. I looked on my record. This is the 5th time I've spoken here, and the redwood forests have always been a charm, and this campus, if you don't know it, is one of the more beautiful places to be and to study. And I've also been charmed by the community here. I'm curious, among that, how many are computer science students, faculty? Engineering, digital media or media studies, what else? Other sciences, engineering, what have we got? Linguists? Statistics. What's that? Statistics. Statistics, great. What else? Psychology, wonderful. Anything else? Astrophysics, great. I love the diversity. My background's in database and file design, optimization techniques, and very traditional computer science, but I like to say I become 20% of an experimental psychologist in studying the way people use the technology, and that's led to the insights that sometimes led to successful technology. So that's great fun, and I'm also very proud of my participation in founding of the Human-Computer Interaction Lab, which this year celebrates its 32nd anniversary on its 4th director. It's an interdisciplinary community between computer science and the College of Information Studies, the rapidly growing one. with psych, sociology, education, journalism, and the wonderfully titled Maryland Institute for Technology and the Humanities Myth. You can go on our website and see our 750 technical reports, 200 videos, 150 project pages, and software, etc., or this cute video done by the campus. Some of you may know me, I hope, from the book Designing the User Interface, which struggling now to produce the 6th edition. The 5th edition was forced by the fact that the emergence of Twitter and Facebook. Can you believe there was one time when there was no Twitter and Facebook? It's just sort of hard to imagine a world like that, but that was not so long ago. And you know, Wikipedia and YouTube were small events. And so the need to address that, and ever more strongly, the 6th edition will even raise to prominence the social nature of technology. And to me, that's a great success story of human-computer interaction, is that we've come to see much more clearly that the computer is a medium for communication among people rather than a machine that solves our problems or does our work for us. It is a tool with no more intelligence than a wooden pencil, I would say, to provoke a few discussions, or a light bulb maybe, it serves us in virtuous ways that are becoming more clear. Even as the tools become more powerful, we're more clearly focused, and that's really the underlying theme of the centrality of human decision making in using these technologies. And so that's really where we're going. I'll just say a moment about HCI pride. We have some sense, I mean, Gordon, Moore's law and Gordon Moore's efforts, have done a great deal, over the years. But the fact that 6 billion people have something like this in their pockets is due not only to Moore's law and the rapidly improving and lower cost of technologies, but also the design of those interfaces. And some of you in this room and my colleagues certainly contributed to that. And even things like Slide to Open, my colleague Catherine Plaisant was the person who created that. And touchscreen keyboard was my work with grad student Andrew Sears. And so these things have a way of traveling and succeeding. And I would say the pride of the HCI community is to have contributed to that in grand ways. And on the mobile devices, the desktop, the web, the cloud, and for all these different communities. That's all I'll say. But it's a flourishing community that continues to grow, and my satisfaction over these years to see its growing acceptance within computer science communities, although I would say every day is still a struggle to make those human dimensions more central to computer science. So today the focus is on big data, and I guess inspired by discussion with Lisa, I wanted to take this a little broader vision on what is big data about. I think big data continues a 2,000-year-old discussion between the rationalists and the empiricists, that the rationalists, going back to Aristotle, believed in if you worked hard and used logic and thought carefully and planned your algorithms, you could make a perfect system. And that theme was certainly continued by Descartes and Kant's critique of pure reason, and continued into the 20th century, where it's had a great run for about 100 years. And from Ronald Fisher's statistical methods to the emergence of statistical tools in World War II, AI, machine learning, and so on, have demonstrated huge power to the careful planning of an algorithm which will accurately represent the world, accurately predict what will happen. On the other hand, it doesn't always work out. Such things as the Google flu trends, which was seen as a grand success in 2009, diverged after 2009. And the failure of that is a fascinating story, which was published in Science in a wonderful 4-page article from earlier this year that you can read about why Google flu trends went wrong and mispredicted the results that were seen as so authoritative, so precise, and so successful. On the other hand, the empiricist tradition goes back maybe to Leonardo, Galileo, the idea that you have to try things out. You have to explore. You have to look at the data. You have to try it. It always needs refining. And you have to look at the data. John Tukey is maybe the hero of that, while a statistician. I'm going to have a quote from him, but he came to understand the importance of looking at the data, understanding the distributions, seeing the outliers, understanding the anomalies, knowing that there are errors in the data, knowing that things are changing. And you're never assured that this perfect mechanism will work in the future. And so we're now at the exciting point where data science methods, both on the statistical side and on the empiricist side, are maturing and having huge, huge impacts. And so that debate continues. And of course, you know, the happy synthesis will be the integration of statistical methods with visualization, the integration of a rationalist perspective with the empiricist one. So that's my grand framing, and we drop down to a little more pragmatic things of sort of my characterization of the start of big data would go to the Obama administration's White House. If you're in the DC area, then politics play a larger role than maybe they do here. And so this 3-page document, which described the Big Data Initiative, has the word visualization 5 times in this 3 pages, but machine learning and data mining do not appear. Statistical methods do appear. And if you know the Washington lingo, data mining became a bad boy term in the aftermath of several political troubles, let's say. And this 3-page document closes with 2 big data challenges. 1, developing scalable algorithms for processing imperfect data in distributed data stores. Great. Okay? We're all for that. That's sort of traditional computer science. That's the algorithmic approach. That's the rationalist approach. Okay? And it fits very well, and it works very well much of the time. The question is, when it doesn't work, how will you know it? And it's one thing when a recommender system makes a wrong suggestion for somebody to follow on Twitter, but it's a different thing when a recommender system prescribes a treatment for a disease that's not appropriate for that patient. Okay? The second is much more the empiricist tradition, creating effective human-computer interaction tools for facilitating rapidly customizable, I love the phrase, visual reasoning for diverse missions. And that's the empiricist tradition, that it's going to put the human in the loop. And that's where I'm going. I want to see that human integration. So here are the cautionary quotes. Ian Whitten and Frank, in all 3 editions of their book on data mining, say exaggerated reports appear of the secrets that can be uncovered by setting learning algorithms loose on oceans of data. And I checked with Ian Whitten. He says, yes, I still believe that. Okay? And then in the National Academy of Sciences report of last year, Frontiers in Massive Data Analysis, attempting to bring statistical principles to bear on massive data may yield results that are not useful at best or harmful at worst. So these are some of the cautionary tales that should remind us that it's not all going to be a happy road, and that we really have to be attentive, because as we move into a world where big data governs many decisions, many activities, not only in commerce, but in medicine and other domains, we have to watch out. So, of course, I will celebrate those who see it my way, and John Tukey's old quote still has value. As yet, I know of no person or group that is taking nearly adequate advantage of the graphical potentialities of the computer. In exploration, they're going to be the data analyst's greatest single resource. And then that same NAS report says visualization and interactive exploration of complex and vast data constitute a crucial component of an analytics infrastructure. So that's where I'm going. Okay? The arguments in the world of big data have been often defined by the statistical machine learning and data mining notions, and that's good. But I am speaking up for this alternate reality, if you will, this other perspective that needs to be integrated. Okay? So the notion of information visualization has been gaining ground. I just attended the InfoVis conference in Paris, which is 20 years going, and we did this book in 1999 with my colleagues at Park, Stu Card and Jock McInlay. Stu gave the wonderful subtitle, Using Vision to Think, that your eyes are not merely input devices to take in colors and lines and so on, but to solve problems, that you, in a few hundred milliseconds, will be able to see things that allow you to spot a problem, see an anomaly, recognize a face. How is it that in a crowded room, I can spot Ike Nassie's face? I can't write an algorithm for doing that. I don't know how I do it, and yet there are many things I can do. Michael Poliani had called this tacit knowledge, and that has a little mystical quality that I'm not entirely comfortable with, but I certainly resonate to the idea that we cannot express all the things we know, especially experts. And the sort of failure of the expert system movement of 20 years ago showed that the exaggerated expectations that we could quantify, taxonomize, and use technical rationality, the rationalist notion, as a way of embedding the knowledge of experts into a finite algorithm. Remember, algorithms are, they may have an infinite number of possibilities, but they're a denumerable number of infinite possibilities, whereas the real world is an open system with a non-denumerable number of possibilities. And so it's hard to accommodate. In 2004, James Thomas put out a research agenda for this area and gave the new name visual analytics. That was a twist on the idea, but suggested that visualization was a tool in a process of visual analytics that goes from collecting the data, formulating the problem, working with others, proposing solutions, presenting results, influencing decisions. And that notion was amplified by our European friends led by Daniel Keim. These last two books are on the web for free, so you can take a look at it. And this 200-page book lays out how many of the current problems in our world could be addressed by these visual analytic strategies. Now, our work has been focused, we had the great pleasure of seeing our research published in '94, become a company in '97. Christopher Olberg led the way. And I don't think I want to describe this, but this is sort of what it looks like. I'll just show another example. These are small ones where we have multiple coordinated windows and, familiar visualizations such as scattergrams. Here we're looking at 15,000 births in Washington, D.C., the age of the mother on the x-axis from about 11 to 52, the age of the father from 12 or 13 to 65. And, there may be errors in the data. We may not know accurately the age of the mother or the father. There may be a lot of incompletenesses here. In fact, there's more than I've shown. I've hidden some of those here. But you get the general idea. The red dots are the girls. The blue dots are the boys. They're size-coded by the birth weight. But there's 40 variables in this data set, and you can control them and filter and so on. Here we have a repeated bar graph that shows the race of the mothers, and there's a lot more to discuss. These dynamic query sliders allow you to filter, and all the windows change at once, okay? This is what real data looks like, 27 windows where one slider filters all 27 at once, and you get to explore high-dimensional data by a series of low-dimensional projections, which tend to be more meaningful. The idea of encapsulating all the high-dimensional data in one beautiful graphic are, sort of a passé idea. The idea that 3D somehow helps is not proven to be fruitful, but the multiple two-dimensional ones are in harmony with our cognitive skills and enable us to see things in a rapid and comprehensible way. I'm not here to talk about Spotfire, but there's lots of other places and where high dimensional or let's say high-res displays are increasingly common. Maybe I'll just focus on this one. This is the standard Bloomberg terminal. If you haven't seen it, there are 300,000 people who pay $20,000 a year to have that on their desk, okay? And the data that's provided, the visual displays and layouts, although I think some could use improvement, the spatial stability, the coordination among multiple windows, the continuous feed of data make this such a valuable tool that 300,000 analysts or their companies pay that, figure it out at $6 billion a year. So that's a pretty serious success story, and it's increasingly apparent that the right design of visual displays can help people work together and solve ambitious problems. This kind of control centers are becoming increasingly common. People working in pairs, people working in groups, sharing some information, having some on their own, and the design of these spatially stable, rich environments, information abundant, I would say, is a major challenge of our time. You can go small as well. In your pocket, my most common visualization is as I'm leaving campus in the afternoon, I put on this app, and I'm looking for big data. I'm doing big data analysis, and what my result is 15 red pixels on the beltway that tell me I should take another road. Okay, and in about 10 seconds, I can get that done, and my decision's made. So big data can be a large engine behind a modest display. While I'm in favor of big displays, there's lots of ways small displays can work out as well in many different fields. This tree map shows every job in America on an iPhone display. It's a hierarchy. We'll take a little more look at tree maps, but that's the kind of scale you can get, and you quickly get the overview. There's a small fraction of government jobs, goods, but services are the big one, and within services, leisure and hospitality. Can you see that? Almost. Is the big field, and also by its dark color, the more rapidly growing one. So you can encode a fair amount of data using size, position, color in a visualization. You can also overload it and make it too busy, and that's another danger. And so there's an element of design that I've come to learn over the years that is still a form of education for me. I couldn't resist, that slipped to the next slide, but we've been working at Maryland to bring visualization across the curriculum. The Campus Visualization Partnership, now more than a year old, supported by Yahoo and actually Google as well. And the goal is to make Maryland a national role model for use of visualization across the curriculum for research and teaching. So we have a broad vision, not just computer science or engineering, but journalism hired, how good is this? Journalism hired Nick Diakopoulos, a computer science PhD from Georgia Tech, to be a faculty member in journalism to do computational journalism and interactive storytelling in journalistic environments, okay? And I see that as a direction, a promising direction, because the power of visualization combined with the idea of storytelling has great potential for informing us about the complexities of the world around us and helping lead to, we hope, better decisions. Now, the expectations are maybe unreasonable, that one visualization will solve the Middle East problem or bring water to California, and you know, those exaggerated expectations are kind of charming to see, but the reality is much harder. And what I'm here today is to encourage you to help contribute to that path and to see that visualization tools are built in a way that enable not just domain experts or computer science PhD or even bachelor students, but the wide variety of the population, that the idea of computer literacy become broad in the population. And my encouragement from this, we ran 8 lectures last spring and another 8 this year, and we've been sold out. And you know, from across the campus, all 12 colleges represented by the audience. That's why also interested to see who was here. But there's amazing pockets of interesting work at Maryland, and people first were just charmed to meet each other, and I'm sure there are here also, where there are people working and applying visualization in good ways. So, okay, so part of that was giving not one big wall in a special room, which is the current popular practice of caves or viz walls, but to give every, you know, not every, but to make widely available high-res displays. So here's what 16 megapixels look like. Each display, these are only $500 displays. They're normal Dell displays. And I will come to my office to write, because I can see 8 pages of a paper. I can actually see 15, but it's pretty hard to edit. I tend to set it up to work on 8 pages at a time, and then I can see my email, the comments made from others, reviewers' reflections, and then make the changes, see them in context. So only for those simple text-oriented things, I would say there's an argument, which we have some evidence for, that your productivity goes up linearly with the number of pixels in front of you. So that's an argument to get a double or triple screen, do it. There's a danger there, of course, that you misuse it and that it then keeps LinkedIn, Facebook, Twitter all open and you're constantly distracted. So as we have more potential, this is a classic human dilemma, as we have more opportunities and more potentials, how do we maintain a focus and concentrate on accomplishing our goals? The recent history of promoting interruption workbenches and ways in which we can provide as many interruptions as possible, we'll probably get one popping up here any minute, is counterproductive to that maintenance of clear focus for the human problem solver. And the simple capacity to see 8 pages without having to scroll and then page down once to see the next 8 pages has enormous payoff, which we've again demonstrated in empirical studies, in one case with physicians making medical decisions about choices of medications. The fewer scrolls they made, not only was they faster, but they made fewer mistakes in choosing the right medications. So the even lightweight idea of a scroll, one scroll to get to the next page, really undermines dramatically the concentration you bring to the tasks. In fact, in the studies done show that sometimes people get distracted and they never come back to their task, or it takes many minutes for them to do it. Okay, so what did we learn over all these years? I playfully wrote this down once, and it's become a bit of a joke by now, but I called it the information visualization mantra and put it just this way, 12 times repeated in an article. And that article has, in a, I would say, second-rate conference, has now acquired almost 3,000 citations on Google Scholar, a remarkable number. And mostly they're complimentary and supportive, and people applying it in different ways. But of course there are people who argue against it, and people who want to flip it around, details first and then go to overview, and there are people who argue against it and people who make jokes about it. But I would say it's gained a certain credibility for a few reasons, I would say. First of all, the idea that the user sees an overview of all the data, whether it's 1 million or 1 billion items, some way in which it's summarized so they see the range of data, the relations, the clusters, the gaps. Gaps are one of the more interesting aspects of visualization. We'll see in a while that you can see a gap, but it's pretty hard to have a statistic for finding a gap. There are 4 papers I found that was gap detection in high-dimensional data, but I still think the general idea of algorithms, Lisa's copying this down for her next paper, but I think gap detection, understanding what constitutes a normal pattern, and then finding the gaps are important. Even harder, if that one's too easy, look for sparse areas. What do we mean by sparse areas of a display? Okay, and then the user zooms in on what they want, filters out what they don't want, and then clicks for details on demand. And this simple idea encapsulates, again, this, as I said at the opening, the centrality of human decision making. It's the human who sees an overview and gains an understanding of the distribution of the outliers and of the errors. Errors are one of, I would say, InfoViz earns its pay just from finding errors in data. And I'll give some examples of this. All right, so here's my overview of the field. We have a 50-year history of success for scientific visualization. Alex Pang here is a credible, important source for that, but many others who have worked on 3D and other visualizations. Of course, the Hollywood animations and video games are another success story of 3D interactive graphics. The new kid on the block is the InfoViz, the multivariate temporal data, tree structured network, and text. And I could go at length. I'll focus on the temporal and say a few things about the others. And on the bottom is a list of some of the blogs. I mentioned flowingdata.com is the work of Nathan Yao. Every morning, the coolest viz of the day appears on his blog, and you can follow those and many other lively discussions. Manuel Lima's Visual Complexity book, Stephen Few's Perceptual Edge, deep, thoughtful blogs, and DataKind, aligned well with Lisa Gatura's Data Science for Social Good. DataKind is a growing movement which is devoted to applying visualization and data analysis and data science to social good. We began with temporal data of the normal kind, and some of you may have seen this, or it's free to download, just time series data of genomic data and stock market data. I think I'll skip over this, and here's where I want to go to, a different kind of temporal data. The great news is when you start looking at data carefully, you start seeing the subtle, maybe not so subtle discriminations. So this was early work to show a single patient history on one screen. And the top is the physician visits, the hospitalizations, the lab tests, the medications and other treatments. If you click on the sonogram, you get the details on demand. So the overview remains here. You can zoom in. We're zoomed in on just 3 years. The design goal here was a 100-year patient history with 10,000 medical events. And here we're zoomed in on a 3-year period. Click to see the sonogram. There's the fetus. You read today. The gray line is today. Patient has been pregnant for 7 months. Forecast to be pregnant for another 2 months. Diagnosed as diabetic by these blood tests. Given insulin, increased dosage of insulin, and then Lasix or Lasix, I'm told, to counteract the side effects of that heavier dose of insulin. So the knowledgeable viewer gets an understanding of the overall picture, can see patterns here, and here again a nice pattern of repetition. Every year this compliant patient has had a pap smear. It's a good thing. But over here you see 3 mammograms in a short period, and then you see no other mammograms. There's a gap, okay? Or that stands out to me. I hope it's dramatic to you as well, but there's a surprise that there's no further mammograms, especially because there were 3 in a short time, suggesting some problem. We look up to the surgery line. We don't see mastectomy, so that's not the reason. We can rule that out quickly with a glance of the eye. No scrolling, no typing, just a quick look. And then we're left with trying to understand why. So maybe this patient got treatment at another hospital, and one of the problems in the current American system of electronic health records is the fragmentary nature and the lack of integration and interoperability. And so these kind of patterns and unanswered questions often come up in the data. But I like this example because it reveals the idea of here, clear cyclic pattern, temporal pattern, and then here a gap that's pretty dramatic. Any questions about this? Yes, thank you. I'll just take a pause.
Just a quick question. So the timeline there is linear?
In this case, yes.
But did you consider what it would mean to actually have some kind of ultrascopy where more detail on more recent events?
Yes.
And what was it for?
We didn't do that. You may know an early paper by our good buddies, Pausner and Ed Tufte. I hope you've heard of Ed Tufte's work, but Tufte's, book on this, 4 books on this topic are certainly one of the defining volumes of information. But they had one which showed a logarithmic view. So basically, you had everything that was older than a year, that was very compressed. Then the last month was, and then the last few days were more clear. So That was a static on-paper version, one sheet and one little timeline for each variable. So there's different ways to work it, and logarithmic scales for time are convenient to the well-informed viewer, but they're misleading to many people. And so there's some real dangers there. But you raised the very good question of how do you deal with large amounts of time, large amounts of data? How does one filter?
Especially in the medical domain,
Exactly.
where most recent events are arguably more important for what the doctor may need.
If we're talking about a clinical support system, yes, that's right. The more recent events. So what's more recent? Sometimes an old surgery might be important. Sometimes a childhood disease could be important. And so there's a lot of domain specificity in these decisions. And I'm going to keep returning to that theme. I hope it's one you'll reflect on, which is that doing these things straightforward algorithmically across different domains just seems dangerous to me. And that the domain-specific adjustments necessary are really important. Now, they could be made by experts in the domain and then have a lot of users who them, or it may be possible to allow local users to make their own adjustments. The diversity of application domains, and within that, the diversity of tasks addressed by users is enormous. I'm constantly, what can I say, encouraged, challenged, troubled in all those ways by the diversity of tasks that real practitioners have to face. All right. Anything else about this one? Oh, in the back, yes, thank you.
I'm curious. So this is visualization, but aren't you just thought of in terms of temporal event detection, right? And you could think of the preceding discussion, sort of a hierarchical or contextual understanding, if you will. But it seems to me that overlaying visualization with the actual underlying analytics may be powerful as opposed to just visualizing alone. I'm sort of curious what your thoughts about that.
I absolutely support that. My opening statement was exactly, we're on the trail of integration of statistical methods with visualization. And here I haven't shown too much. There's a rich control panel. You can see some of it here. It allows some flexibility, but in our early thinking, we didn't explore that in great depth. We allowed some controls, but not statistical modeling, not comparison with similar patients. There's a lot of other possible things by which one make predictions. Minimalist predictions like predicting a pregnancy to continue are a kind of safe space, but statistical predictions were a different story. I'll take one other short question.
Yeah, really quickly. So you said that there are so many very important subtle differences between domains. What about programmability? So,
Yes. This had a moderate degree of programmability and extensibility. There was flexibility in choice of colors, in the coding mechanisms. There was a sort of input data format. I didn't show even the text searching or other kind of capacities. There's a variety of filtering. These different domains can be collapsed, so you exclude all the medications, or you look only at blood tests, or if there's a lot of them, you look only at x-rays. And so there's a rich degree, and I believe that's an interesting and non-trivial point, that the power of visualization is the capacity to explore and make sense, whereas statistics presents an end game result that limits the backtrack explanation to understand. I mean, I don't know if I need to show Anscombe's quartet here, but Anscombe, famous statistician, showed that you could have the same statistical measures for, there was 4 graphs he made that had very radically different patterns, linear, quadratic, random, and so on. And then he showed they had all exactly the same statistical properties of mean, standard deviation, correlation coefficients, and that just having the statistical results often hides. That's what we've seen before. So the capacity to explore is really what I'm getting to. We'll get to more of that. So 1 patient's great, but 1 million patients is better. And I think I'll cruise past our intermediate steps, but go straight to the demo about event flow. So this is our current work that I want to show you. And I hope my highest expectation would be somebody here will say, hey, I have some data that fits for this. Let's work together. And we'd be glad to support. We have about 24 users around the country or beyond. And here is a simple story. It's from Children's National Medical Center, where the pediatric trauma unit receives babies and up to young teenagers who are in trauma. They may be comatose, they may be in great pain or screaming, or there may be a 2-year-old who can't express himself or herself. And they have a strict protocol of what happens when a patient, the ambulance arrives, the team assembles, and they go to work. And the story is you check A, B, C, D. Check the airway, is it clear? Check the breathing, check circulation, check disabilities. All that has to happen in 2 minutes. And then you get 7 minutes for the so-called secondary survey. Take the clothes off, turn the baby over. Are there bruises, wounds, bleeding, inflammations, abrasions, or anything else? Check the whole body, and that you get up to 7 minutes. So the staff was interested, the management was, how often does the team adhere to this protocol? How well do they do it? And more importantly, when they miss, what are the ways they make mistakes? Okay, now you could start conjecturing all the possibilities. I think you could imagine that some events don't get done, some get done out of order, some get done with long delays. It could be a variety of things that happen here. They set up a video camera in the trauma bay and videotaped 215 admissions, and then someone visually went through and tagged them all. Now you can imagine all kinds of problems with this. But, you know, here's the way we're going to look at them. And that's, I'll go to the demo here. So this is Event Flow Live. And here are the different events they tagged in the data. And you can see what we call the confetti view. It may be very pretty, but it's not very informative. And there's just too much data going on. This is the aggregated view. This is the individual patient view. We could scroll through, and you could see some of the things that are happening. Sometimes a secondary survey gets done promptly or very promptly. Sometimes we'll find an example of a secondary survey that takes a really long time. Sometimes we'll find one with a really, there you go, there's a really long time. And, you know, this allows you to browse the individual ones. Now, this is a small data set of 215 patients, but already it's overwhelming. And the usual relational models just don't support this, and I know of no SQL, you know, temporal SQL variation which lets you do these kind of things in a reasonable way. Expressing queries against this is quite difficult, and viewing the results is even more confounding when the results are a relational table, because even principles of before and after take many seconds to spot, is this time later than that time? Or if I'm asking complex questions like during the secondary survey, did something happen? And we'll see how we can make those kind of explorations quite easy. All right, so there's a lot of data here, and it's a little overwhelming. So I'm going to start in a different way. I could start deleting things. We're not interested if the patient got an IV or received a blanket or got oxygen. So we could do the deletion scenario, which might be good. But I'm going to start the real simple way. I'm going to clear the screen. And I've told you ABCD, secondary survey. That's what we're looking for. So let's look at just a little at a time. Let's get a simplified overview. Airway check, breathing check. Okay, now I hope I've given you enough of an explanation. You can see what's going on here. That from these 216 patients, we can see that here this group got the right A and B. Airway and then breathing, and that's the distribution of times that they were captured at. So, you know, it's pretty good. However, even here, right away, our eye is brought to this attention. These are out of order. And when they're out of order, they take on average longer. There's obviously some confusion going on and the right thing didn't get done. And if we zoom in, we will see there are 5 patients who didn't get the airway check at all. Okay? So even this very simple thing with just 2 categories of events already, I mean, one might imagine writing algorithms that would check for these alternatives, but there's such a prolific explosion of the possible combinations that the visual presentation, I will argue, gives you a quick insight to seeing what's going on. All right, let's go add the next. Central pulse, we're checking, and it turns out there's 2 kinds of pulse. There's distal pulse and central pulse. So distal is here, central is here, and for some of these patients, you can see they got the ABC, airways, and then onto the distal pulse. Some got just the central pulse, some got both. All right? So we now have additional complexity in the data when 2 things get done, and then you're beginning to see the variety of way things didn't go the way they were supposed to, okay? And we're getting a slowly growing combination of all the funny things that happen. So let me show off a few of the features here. First thing I'm going to do is combine the categories. The central pulse and the distal pulse, I'm going to call that any pulse. Whoops. So I'm going to make that register as any pulse over here, okay? And I was using green, so I'm going to stick to my green, and we'll make it a bright green. Now again, we see the double ones here, and I'm going to show you the simplest possible search and replace, graphical search and replace. I'm going to say if I get an any pulse event, and anytime after that I get another any pulse event, I'm going to replace that with just the first occurrence. It's a really trivial one, but I just want to assure you that rich ones can be applied as well. So now those go away, and we now see a pretty good story of these people mostly getting A, B, C, A, B, C. Okay? We can see here somebody that got A, B, but didn't get C. Here they got A, C, B. Okay? And so you begin to see and understand what's going on here in this data set and the ways in which it violates the domain-specific explanations. All right, let's go on to disability. A, B, C, D. All right, pretty good. We're getting that mostly happening in order. You can see some violations where that happened earlier. Maybe better to point here. Mostly things are going okay. We have some funny out-of-order sequences. We know about the 30 patients who had the breathing and the airway backwards, and we continue to see those. And now let's add the secondary survey, which should happen afterwards. And there we go. We see right away one outlier, which is a secondary survey that took 27 minutes. Okay? And that's clearly a problem. And let's just zoom in on what's left here. And the good news is, well, semi-good news. 105 of these patients, 104 got A, B, C, D, and then the secondary survey. Actually, I find the secondary survey, let me make that a little light pink color so it stands out a little better. I think that makes for a better view. All right, so we can take the ones that are all right, the 105, and let's remove them. We'll hide that selection. And now I see the 29 kinds of ways in which the protocol has been violated. Can you see the most common violation? They're stacked by the most common going downward, so it's right over here. The disability was done after the secondary survey was started. Okay. Now, again, this is a very simple case, but it's one that I hope will convey the ideas of event flow and its utility not just for patient histories, but for weblog analysis and social media analysis, cybersecurity attack sequences, and so on. And I've shown you a tiny fraction of the features in Eventflow, but they're always attuned to what we learned from our case studies with real users, real problems, and real data. That's our mantra. We work with real users, real problems, real data. Not our laboratory imagined theoretical possibilities, which are vast and interesting and offer many challenges, but we write the minimum amount of code to solve the problems our users bring to us. Okay, that's our sort of working philosophy. And we can see the many other ways it was, violated. Maybe one thing to look at, we could do alignment. We could align from the beginning of the secondary survey. So if you have a particular event, you can now make that the alignment point, and you can see all the things that happened before and after. And there's that violation that we see so commonly, that the disability check was done after the beginning of the secondary survey. Now, is this terrible? We don't know. The researchers have gone back to recollect more data and also track whether these variations or which of these variations meant poorer outcomes for the patients. And so I would say the majority of times we're involved is that what it leads to is to more refined approaches to collecting data and cleaning up the data. The majority of data sets I get to see have things wrong in it that those applying statistical methods only were unaware. I mean, one of my favorite stories is the 6,300 emergency room cases that were brought to us to study, and they were doing the average age of the women and the average age of the men, the average age of those admitted and discharged with insurance, without insurance. Little did they know that 8 of those patients were 999 years old. Okay? You know how that happened. It was a code for we don't know the age. Okay? But the routines that did the statistics were not tuned to that. And it's not that there's a finite number of kinds of errors. I would say, again, there's an open, non-denumerable number of kinds of errors. So in that same data, if you did the distribution by age, you would find a preponderance of those who were 25, 30, 35, 40, 45, 50, because the doctors didn't know and they guessed. Okay? You will also find a large fraction of people under 1 year old, especially mysterious result. It turns out, of course, when entering the year of birth, they happen to enter the current year. And so you get a lot of people who are under 1 year old. And the gaps, I've got a year's worth of commercial data, of e-commerce data, no April. They had no idea. They're building predictive models, yet the key Easter season is missing, okay? The emergency room. My favorite story is the patient they were trying to estimate, learn the average number of days spent in the emergency room for different classes of patients. Little did they know that, the extreme case was one patient who was admitted 14 times, but discharged only twice. Okay? Now, if you think a minute, you might even guess why that happened, because admission is a billable event. And so it gets recorded quite accurately, whereas discharge, not really, and sometimes it gets left out. The 14 and 2 is an extreme case, but I assure you there are lots of kind of anomalies like that. And I would say, in our work, whether it's 6 days, 6 weeks, or 6 months are spent cleaning the data and cleaning it again and cleaning it once again, because the number of funny things that go on are staggering. I had the pleasure to work with Lisa Couture on the Dedupe project, where in the paper you can read there were 3 supposedly trusted exceptional resources of bibliographic data, right? And from our major professional societies, and we found many, many errors in that data. Okay, I could show you lots of features. I guess I guess there's a wonderful, and maybe the most interesting paper to read is the graphical search and replace, where the idea of having a simple operator like while. So search for, during the secondary survey, how many patients received or were, had any pulse event, okay? And I can, whoops, I lost that. But the creation of a during event is a quite interesting one, and we can search and we can find all the cases of patients here which had that, of which there are 21, and 194 did not have that match. So the capacity to find, for example, patients who had a stroke while they were taking warfarin, or within a week of the time they stopped taking warfarin, is one of those powerful features that's extremely difficult to express in SQL or other languages. Or find the patients who were, try writing this in SQL, find the patients who were admitted to emergency room 3 times within a month. Okay? If I give you the query 3 times within January, that's easy. But 3 times within a month, you'll find yourself with multiple self-joins that will make your, unless you have a very cleverly optimized design, it's going to run for a long time. Okay? All right. I will, unless I see a question about event flow. Yes?
So I'm assuming that for these queries, you have specific data structures.
Yes. These are all high-speed storage data structures, paper published about the data structure. They're faster than any regular expression algorithm for doing similar kinds of things. They're also applicable for genomic exploration and other things. They're very fast. They have some problems of scaling to the number of diverse events, but we've done okay with that. And they do pretty well scale to the length of the streams of events as well as the number of records. But you do get problems when you have many, many, many categories of events. And there we've sort of focused on ways to we call sharpen the analytic focus. So here, one example in the ICD-9 medical diagnosis categories, there are 400 forms of lung cancer and about 200 forms of bone cancer. And that's quite confusing because you have all these different kinds. However, if you aggregate all the lung cancers into one event type and all the bone cancers in another, you will quickly discover that lung cancer often spreads to bone cancer, but rarely does bone cancer spread to lung cancer. So the capacity to sharpen your focus is the central thing, I think, in making visualization friendly to big data. The capacity to clean, filter, organize, and extract the data is really important. We work with the Army Pharmacovigilance Center, 15 million patients, 35-year history, tens of thousands of events per patient. But any particular task might be to study asthma. Only 182,000 have had asthma medications. And for those asthma patients, I don't want to know if they broke a leg or if they've had some other diseases. So I focus on the asthma-related events. And then if they've gotten 40 months of asthma medications, I don't want 40 events. I want to see a time period on which they were a certain asthma medication. So the ways we simplify, clarify, not just to deal with scalability, but to deal with clarity, to focus my lens on the issues at hand. All right. I'm going to yes?
Going back to event flow, I'm curious, do you have a p-trend here? Because I can see we can get like an aggregate of all the temporal data to be able to see like, oh, did A come before B and all this. And we can see where there was mistakes, but are you able to analyze all of that on a bigger time scan to see like, oh, well, maybe these mistakes happened earlier in the history of this hospital, or later due to some training or something, and see where it was actually.
I mean, we do follow this sort of parsing left to right, and we do work from the basis we can adjust that parsing to align by any particular sentinel event, like when they had a stroke, what happened before, what happened after. But it is a real problem of what you suggest. If you have some complex pattern like AB and then string of hundreds of events and then an AB later, finding those together is tricky. That's the next stage called COCO. That will look for those common patterns. And particularly, I'm just advertising the current research is on cohort comparison. If I'm getting a stern look from Lisa. So the cohort comparison task says I have 100 patients, 1,000 patients who died, 1,000 patients who lived. What's similar? What's different? And that's very hard to do in any kind of method. Most clinical trial data, you have simple, t-test comparisons of outcomes, and we can look at the sequences of events, and we're getting it. That's the PhD work of Sana Malik. All right, I think I'm going to cruise by here. Tree maps, aren't they wonderful? You can see the good and bad news. I think I'll just can't resist going to my final networks. Node Excel, thank you, Lisa. Try Node Excel. We have 330,000 downloads. Join the crowds. And some of the things actually simplify data in this is Illinois. I can't resist showing this beautiful, recently Illinois Innovation Commission used this Node Excel image to show the relationship of universities to businesses in the Illinois innovation infrastructure. And I'll just cruise past all that. And just close with this, I promised this sort of my attempt at 8 golden rules of data science. Some of you may know the sort of the famous sort of 8 golden rules in my book that's been widely cited. So, I would say that the process of visual data science or any data science should include focusing on actionable problems and start with compelling theories from the domain-specific area. Understand the domain. I don't believe in doing data analysis without understanding the domain. You can try, but you're at great risk. Open your mind, so domain experts and statisticians. And then, if you don't have questions to get started, you're not ready. I mean, we get companies that say, I want to visualize my data. I say, what's your question? I don't know. I just want to look at my data. I say, come back when you have a question. Okay? Not that the question they ask is going to solve everything, but having a question shows a deeper understanding, concern, commitment, and engagement with their data. And then, clean your data gently on the screen, merrily, merrily, merrily. Data science is just a dream, right? So I just can't tell you how many times the surprise. When we show our domain experts the visualization of their data, often the response is, oh, there's a bug in your program because this never happens in reality. And we go back to reality and we find out actually it did happen. The patient who had 219 creatinine high tests was so outside the range of their expectations, yet there it was in the data. And again, the surprises in real data, maybe especially medical data, but lots of other, even data from sensors and stock market data that you think's been cleaned, or scientific data from legitimate associations, still has problems. And then get to know your data, the ranges, the patterns, the empiricist's admonition, know thy data. And finally, evaluate your efficacy and refine your theories. Take responsibility for your successes and your failures. Too often, Nate Silver's book is quite wonderful about identifying the overemphasis on not just confirmation bias, but of people remembering their successes and not their failures. And if you want to do an honest job here, remember the world is complex. Proceed with humility. And as I stressed with some of the student groups this morning, work on real problems in the real world. The talents you have, the tools you have, make it possible for you to actually help in solving real problems. So in our theory of problem selection, think carefully about important problems. Distill from those very solvable, actionable goals that you have. And then come join us for our 32nd annual symposium, May 28th. 2015, or join us on the web, or follow me on Twitter. Thank you for your time and attention. And I know some have to go, but I'm glad to take questions.
Yeah, so there's time for a few questions. So, questions?
Yes, thank you.
visual analytics. So the reason why I ask this is because we tend to see what we want to see. Or I sort of put it a little bit more broadly, we work with a lot of cognitive biases. An example of this is just, you cited Tukey at the beginning. You know, when we think we see a pattern, in fact it's not a pattern. And so there's lots of areas in psychology, social psychology, that study cognitive biases and show really that we tend, like if we take an approach like I think you're taking, which is Douglas Engelbart put it as augmenting human powers, right? We augment those human powers, but we also exacerbate sometimes those powers. And so a lot of statistics is set up to cross-check that. Or another way to do it is if you augment two different powers, let's say vision and hearing, then one cross-checks the other. So I think some of the examples you were giving here is that no one had ever seen their data. They've just seen it textual. So if you put text and vision together, you're cross-checking and making one an error checker for the other side. So statistics can step in and help you counteract your cognitive biases, I think. And so how these two go together, the visual analytics and the cognitive and the statistics seems really key.
Thank you, Warren. There's a lot of things in that statement. You were asking first how to put them together, and then you were alluding to the dangers of visualization, and you're suggesting that statistics provide a check on visualization. And they do. At the same time, I would say it goes the other way. That visualization provides a check on statistics. I am advocating doing both. Okay? Now, we can have descriptive statistics, which is a good place to start, and never give up on that. It's sort of the fundamentals. What's the means? What's the standard deviation? What's the range? Etc. Okay? Look for correlations. Look for linear. Look for quadratic correlations. Okay? Statistics can lie as well. I mean, you find correlation coefficients which are misleading, or you find no correlation, but there's actually a strong quadratic correlation. Okay, that's the Anscombe's quartet. If you look it up on Wikipedia, there's a great example there. But I do think these go together. So you learn from each and should know the strength of them. Not to say that either the rationalists or the empiricists, not the statistics or the visualization, but both together. And, you know, we are, I would say, at the beginning of integrating predictive models into the visual domain. That's kind of the current issue. And actually, we could stretch even to the more bold issue of causality in big data. There will be a workshop or conference at the National Academy of Sciences in Washington, March 26, 27, about causality in big data, another sort of dangerous place to go. But do you want to reply to that? Is that?
Well, I guess, yeah. I think we've agreed.
Okay. Okay. Yeah. So visualization is a new tool, and it does require certain training in visual literacy to know that certain color palettes are misleading, certain ways of using size or proximity can be distracting or give undue emphasis. I would say also remember statistics. Clustering. What can we say? Clustering is a famed statistical method. We use it a lot in Note Excel, but it is similarly seen as a black art. That false clusters emerge from statistical methods. False predictions emerge from predictive modeling. And so, I mean, cautions, that's not, you know, my closing line about humility is really important here. And whatever you can do to check yourself by using these multiple methods and by consulting domain experts and statisticians, you should do. Just be careful because, again, when we're using big data or other things to make Amazon recommendations of books you might want to look at, a mistake is not serious. But when we're talking about more serious, life's critical applications in medicine and law, finance, high-speed trading, we should be aware of the real dangers. And I'm very much for the responsibility, the clarification verification of responsibility, logging of what's happened, retrospective analyses, so you can track what's going on. And I guess a little bit far, but coming back, and I would say bullet visualization statistics have that role. I mean, try to make that very clear.
A word about my motivation for it is I see more and more fields showing as results some kind of information visualization that is not cross-checked by some other modality.
Are you not worried about fields that are using visual statistics to present results without cross-checking, for outliers, for bimodal distributions, for gaps in the data? No. I mean, that's kind of an accepted missing part of our analytic workflow. All right? So I would say, caution about statistical tests. Errors in the data, omissions, redundancies. I mean, one simple 1,400 row spreadsheet had 81 lines, exact copies of another 81 lines. The number of ways errors creep into data is frightening to me. Mature institutions like NASA has a 6-stage cleansing process for its remote sensing data. Okay? And so we really need to work it through, and it takes a lot more than you think, even when you have what seem to be trusted resources. Other questions? Yes, thank you.
Actually, to pick up on that question, we can't really do data analysis anymore without using other people's data, right? So are we responsible for checking everyone else's data, or is there some way you can certify data sets so that we're not all checking each other's data?
There are ways, and there's increasing families of curated data sets, from genomic data to U.S. Census data. Certain organizations gain respect because their quality control metrics, Library of Congress, Census Bureau, in general are more trusted resources than if you go to some, fly-by-night website that you've never heard of. So there are sort of social situational ways. I don't know that there is I think that's a really interesting idea. Could you have a family of tests that could be applied, a kind of certification? And if you pass all these tests, you get certified, and it's sort of trusted for doing the following operations. Would be a nice idea, actually. Still, again, even there, the number of ways, I would say, I wanted to write this paper. If somebody wants to do this, we could, which enumerates, even for simple numerical data like age ranges, all the different ways we've seen of failures, and all the things we might then write to check. So we get a large number of these, and we could write R or other statistical things to check for those, and we reduce some of those problems.
Yeah, I was also thinking about like papers where you have results, running on complex methods. Many times you can't reproduce the result.
Yeah. Well, increasingly, journals like Science and Nature require you to have an accompanying website where your data is placed so that others can review and use your data. The questions of curation of those data sets over long periods of time across different formats, etc., remains an enduring challenge. But I think, yes, quality data will be important. And I just want to add to that. Almost every problem we see, you start with one set of data, and then you say, well, I actually want to integrate this other set of data with it. Okay? And then you get these problems of the links don't quite work out, and everything's not quite the same, and there's just proliferates. I mean, if you want an example, the census data is pretty interesting. Okay. But the simple question of I'm planning to move to either Colorado or Florida. How about the cost of housing? And how would you compare houses in Colorado as opposed to Florida? What is a 2-bedroom versus 3-bedroom house? And in Florida, is a closed-in porch a bedroom? Which it wouldn't be in Colorado. So do you know what there's a 1.5-page description of the Census Bureau to describe what a room is. Do you know what the 2 key things are? A bedroom, excuse me. A bedroom must have a closet and
door.
A window. If you don't have a window but a closet, you've got a den. Okay? So the descriptions of these things over time, and at some point, the rules have changed. So before 1961, this is what we mean by a room. After 1961, this is what we mean by a room. Now decide to show me a curve about the cost of rooms over a 100-year period. Okay? These dilemmas are real, pervasive, and important. And if we're going to make a data-driven society, which I'm all in favor of, and we're going to promote a respected data science community, we need to address this. Thank you.